Yeah, hello everyone. It's our pleasure today to have Isabel to talk about her recent work on symmetry invariants like quantum machine learning force fields. Yeah, I first heard of this work like when I was in QTML, and I think this is quite a nice work for our community to know about it. And yeah, Isabel will be able to tell us more about this. Yeah, Isabel, the floor is yours.
Thanks a lot. Hello, everyone, and thanks a lot for having me. Maybe I'll just introduce myself very briefly. I'm Isabel, and I'm currently a PhD student at Technical University of Munich, where I work with Professor Christian Mendel on quantum algorithms. But today I will talk about my research that I completed last year with IBM Quantum and RWTH Aachen University. More specifically, I will talk about our research on symmetry-invariant quantum machine learning force fields. And I will start this talk with introducing to you the overall setting of this project, which was namely molecular dynamics and some existing classical and quantum models that can already tackle this challenge. I will then talk about the role of symmetries within chemical systems and how geometric quantum machine learning can be used to incorporate these invariances. I will show you the symmetry invariant quantum models that we designed and so also some numerical results that we achieved with these models for exemplary molecules. And then I will conclude this talk with a brief summary and maybe also outlook. Yeah, but let's start by talking about the overall playground of this work, which was molecular dynamics. Molecular dynamics is a computer simulation method to analyze the dynamics of atoms or molecules in a physical system. And the simulation can then, for example, be used to obtain macroscopic thermodynamic properties for an ergodic system. And within this simulation method, you basically numerically integrate the Newton equations. And therefore, it is crucial to have access to the forces acting on the constituents of the system. So the atoms or molecules in the system. Or equivalently, you would have to have access to the potential energy surface, from which we then can obtain these atomic forces. This means that the overall goal is to have some kind of model that can give us access to this potential energy surface or atomic forces. And the classical community has already some tools established for this matter. So for example, we can make use of ab initio methods, such as density functional theory. And these methods describe the atomic interaction on a quantum mechanical level and are hence very precise. But on the other side, they are computationally very costly for the setting of molecular dynamics. So to avoid this computational cost, an alternative method of so-called force fields has been developed. And force fields are empirically found functional descriptions of the potential energy surface. And therefore, they are very easy to evaluate on the fly as it is required within within molecular dynamics. But they are based on approximations and empirical, and therefore are also worse in accuracy in comparison to these ab initio methods. Now, to bridge this gap between computational efficiency and accuracy, machine learning methods have now been employed. And within these so-called machine learning force fields, the atomic forces are learned from a set of reference data without the need of any further approximations. So this means that we have a set of atomic configurations for which we already know the corresponding energy. So this would be the reference set. And these energies could, for example, be obtained by very accurate ab initio methods. And then we train a model to reproduce this mapping between the atomic configuration and the corresponding potential energy surface. So it's some kind of regression task. And this idea of employing machine learning methods for the task of learning force fields has previously been transferred by my colleagues to the quantum realm. Specifically, they have designed quantum neural networks to learn these forces. And I think you all know, since you do quantum machine learning, what I mean by that. But with that quantum neural network, I just mean a variational quantum circuit that kind of looks like what I've depicted here in the upper part. Okay, so this quantum neural network, so the actual quantum neural network that they used for learning force fields is depicted here in the lower left part. And this quantum neural network is such a variational quantum circuit that consists of a data encoding layer, this is depicted here in blue, and a trainable layer consisting of parameterized operations where the parameters are these parameters to be optimized. And this trainable layer is here depicted in rows. And this stack of encoding and trainable layers is then repeated several times, D times more specifically, where D is just an empirical control factor to tune the expressivity of the model. And such a model is indeed a so-called reapplauding model. And you can show analytically that such type of model expresses truncated Fourier sums. Okay, but now let me jump a little bit and talk about symmetries. Because our physical or chemical system shows some invariance under which the corresponding energy does not change. So for example, if we translate or rotate the overall system, the actual configuration of our system stays the same. And if we simply interchange atoms of the same type or also molecules of the same type, the overall system configuration still stays the same. And for larger systems, if we reflect the system about some plane, the corresponding energy is still the same. So when we now think about the forces that we can derive from these energies, it's not exactly the same, because if we just rotate the system, the forces will rotate with this action. So the forces will also change their direction, but accordingly to the symmetry transformation. And this is then something that we do not call symmetry invariance, but symmetry equivariance. And I will also make use of this concept a little bit later when I talk about how to include the symmetries in the quantum circuit. But that means that these kind of symmetry invariances need to be reproduced by whatever model that wants to predict the system's energy and forces. So to do so, the data can simply be made invariant itself, the data that we input. For example, internal coordinates, such as bond distances or angles, are already, by definition, suitably invariant. Or alternatively, we could also construct so-called symmetry functions. These are basically descriptors of the local chemical environment of an atom, and they are designed in a way that they incorporate symmetries of the system, such that if we input them as the description of the atomic configurations, we would have the symmetry invariances already given by the input data. Okay, so this means that we could incorporate the symmetries by means of classical pre-processing of the input data. So we just kind of put the information about the symmetries in this representation of the input data or of the atomic configuration. But actually, this task is not so necessarily easy. It can be difficult to find such a unique and complete configuration to energy map. And furthermore, we would also need to do classical post-processing as well, which might lead to amplified errors. Okay, so again, to phrase it in a different way, we could just put invariant representations of the configuration in, and hence yield invariant energy predictions out. But in this work, we wondered whether there is a way to rather incorporate the symmetries in the quantum learning model directly instead of in the input data. So we wondered whether it would be possible to simply input the atomic configurations as raw data. By that, I mean just Cartesian coordinates of the atoms in the system, and whether it's then still possible to get invariant energy predictions out. Incorporating these symmetries in the design of the quantum model would be physically inspired, would be a physically inspired and reasonable inductive bias, which could lead to better generalization properties. And furthermore, we would also not need to do any classical pre-processing because and post-processing, because we would just directly get the forces with respect to the Cartesian coordinates, such as required within molecular dynamics. Okay, so now on this slide, I want to go through the process of forming or designing a symmetry-invariant quantum machine learning model from a generic quantum machine learning model. So we start from the generic quantum learning model that was designed to learn the forces. And now I want to show you how we have to modify it in order to obtain these symmetry invariant outputs when it comes to the energy. So this means in the end, we want to have a model that predicts the same energy for a configuration X and any configuration that you can get from X via a symmetry transformation that acts on that data level. So here we call this symmetry representation on the data level VG. So that means this is how a certain symmetry element acts on the Cartesian coordinates. And in the following, we will denote the corresponding symmetries action on the Hilbert space with RG. So this would be how this exact symmetry element would act on the qubits. To have an overall invariant model, our variational ansatz needs to be equivariant. So that's something that I've told you before about the forces. The forces are equivariant with respect to the symmetries and not invariant. In the case of the reuploading model, this just means that both the encoding and the trainable layers need to be equivariant. So what does this actually mean? For the encoding layer, this means that applying the symmetry transformation on the atomic configuration and then encoding it results in the same encoding layer as encoding the original atomic configuration and then letting the symmetry act on the qubits. Okay, so that means, for example, if I have a chemical system and I rotate that system, I can rotate the system and then encode the configuration in my encoding layer. And this would be the same as encoding the original system into my encoding layer and then letting the corresponding symmetry representation act on the qubit level. So that would be the meaning of equivariance for the encoding layer. And for the trainable layer, equivariance means that the order of applying the symmetry and these parameterized operations does not matter. So you can, in general, imagine this as pushing the symmetry action from the data level to the qubit level. Furthermore, we also need to find an invariant observable and initial state, which you can imagine as a process of absorbing the symmetry action. And then if we put all these things together, so the equivariant variational ansatz, the invariant observable, and the invariant initial state, then this results in a symmetry invariant quantum learning model as we required. Okay, and here on this slide, I just wanted to show you how these equivariants and invariants kind of lead to actually a symmetry invariant output. So this function is defined as the expectation value of our variational quantum circuit with respect to this invariant observable. And then so this m theta vgx just means that I first apply vg, which is the symmetry, on the Cartesian coordinates, and then I encode it and build the variational circuit. And due to the equivariance of this variational circuit, I can just kind of pull out the action, the symmetry action, and push it to the qubit space or to the qubit level. And then due to the invariance of the observable, this can be the symmetry representation RG can be absorbed. And the same happens with the symmetry action that will now act on the initial state. So this will also be absorbed. And in the end, you just get the exact same results as if you had inputted the original configuration, chemical configuration, without, for example, rotating it or translating it, etc. Okay. So next, I want to show you our architectures for some exemplary molecules. First, we consider a single diatomic molecule, such as lithium hydride. And in this case, the system is invariant under translation and rotations. So we make use of translational invariant input data by setting the origin to the middle of the molecule, such that we don't really need to care about translations anymore. And hence, we only need to take care of rotational invariance within our quantum model. A general rotation on the data level can be represented by means of 3 rotational matrices. This is something that we already know very well. And actually, the same parameterization can be taken to get the representation on the qubit level by now just taking the corresponding single qubit rotations. The singlet state is invariant under rotations, and we can expand this to any even number of qubits by repeatedly tensoring the state. And then next, we also need an equivariant data embedding. So we choose to encode a 3-dimensional data point with this following scheme that I've shown you here, where we also introduce a new scaling factor alpha, which I call the encoding angle. And this is actually a trainable parameter. So this means in how we defined our encoding scheme, the encoding layer itself also has a trainable part. And this encoding scheme is indeed equivariant, since embedding this rotated data point is just the same as embedding the original data point and then letting the rotation act on the qubits by means of their single qubit rotation representation. Okay, so I've just shown you how we encode a single 3-dimensional data point, but for lithium hydride, we have 2 atoms to encode. And furthermore, we choose to encode each atom twice for higher expressivity. And we can do so by simply using the just introduced encoding scheme twice for each atom, as depicted here in this graph, but each on a new qubit. Okay, so for the rotational invariant operator, we take the Heisenberg-Hamiltonian as an inspiration because it is already rotationally invariant, and we define a single summand of it as a rotationally invariant 2-qubit operator. Since this is already invariant, we choose this simply as our observable. And furthermore, we can obtain an equivariant parametrized operator by exponentiating this Heisenberg interaction. So this is how we call our summand. And by combining this exponentiated operator for different pairs of qubits, we can design our equivariant trainable layer. This is also shown here or indicated here in this pic. Okay. So that was our considerations for the diatomic case. We now consider a slightly larger molecule of 3 atoms and 2 atom types. An example for this case would be water. Here, We also need to take into account the invariance under permutations of the same atom type. So in the case of water, hydrogen. And translational symmetry is again included by means of fixing the origin. Here we just set the unique atom into the origin such that we only need to encode the two identical atoms. So hydrogen in the case of water. Okay, as I said, we also need to take into account permutational invariance in this case. So interchanging two atoms on the data level is just represented by simply exchange or interchanging the corresponding coordinates. And on the Hilbert space, this is represented by swapping the corresponding qubits, depending on how they were or how the atoms were encoded. And we can note that the singlet state is not only rotationally invariant, but also permutationally invariant for swapping certain qubit pairs. So we can just stick to this choice as an initial state. And the previous embedding scheme for one data point can simply be extended for embedding two atoms. And we see that this indeed is not only rotationally equivariant, but also equivariant with respect to the permutations, since encoding two swapped atoms is just the same as encoding the atoms in the original order and then swapping the qubits. Okay. Again, we choose to encode each atom twice, as depicted here. So each atom in two qubits, kind of, repeatedly. And for the invariant operator, we note that our Heisenberg interaction is invariant under swapping of the two involved qubits. So therefore, we can make use of the same observable as before. For the equivariant parameterized layer, we need to be a little bit careful when it comes to the selection of qubit pairs in order to obtain equivariance. That means operations that commute with the swappings. This is fulfilled for exponentiating the Heisenberg interaction that act on the first and the two and the last two qubits, each separately. And for exponentiating the Heisenberg interaction that act on the first and the last qubits and the second and the third qubits jointly. So this is depicted here. Okay, so that was our second example of a water molecule. Now we have a third example where we look at a triatomic dimer. So for example, two water molecules. And here, next to rototranslations and permutations of identical atoms, we also need to take into account the interchanging of both molecules and a reflection about a plane, an arbitrary plane. And as before, we include translational symmetry by fixing the origin to the center between the two unique atoms. Okay. So any reflection can be decomposed into a rototranslation, so rotation and translation, and the reflection along a certain fixed plane. So we can now just consider the specific reflection that results in a minus sign on the data level. So a minus sign on the Cartesian coordinates. And the corresponding representation on the qubit level is just given by the poly Z operator. For the equivariant data embedding of one data point, we expand the embedding scheme that we used before and make use of an ancilla qubit where a poly X operator just handles any sign flip that could occur from this reflection symmetry. And to extend this for the encoding of several atoms, because here we do look at two water molecules, right? We apply the scheme for each atom on a different qubit, but with the same ancilla qubit. So we only have one additional ancilla qubit. And furthermore, we introduce an atom type specific encoding angle. So that was already introduced before, but this time we have a different trainable scaling factor for each atom type. And this encoding scheme is equivariant under rotations, permutations, and now also reflections. So this means we have an overall quantum model of 7 qubits now, because we have 6 atoms and 1 ancilla qubit. we choose the initial state as a suitable combination of singlet states, which incorporates the invariance with respect to rotation still and permutation as well. And now we also have a zero state as the eigenstate of the reflection representation on the ancilla qubit, such that in total we have our invariant quantum state. Okay. Since the reflection symmetry only affects the ancilla qubit, we can still make use of the Heisenberg interaction as before, which still includes rotational and permutational invariance, and now just extended by a reflection invariant operator that acts only on the ancilla qubit. So this leads to an invariant observable shown here on the right middle side. And for the equivariant parametrized operator, we can again just exponentiate, but we need to look out for suitable qubit pairs again, such that we can ensure our permutational symmetry. And the overall equivariant trainable layer then consists of the exponentiated Heisenberg interaction for suitable qubit pairs for the first 6 qubits. So this is where we encode our 6 atoms of the water dimer, and a Z rotation on the ancilla qubit. Okay. So to visualize these 3 architectures that I've just talked about before, I have drawn the overall model here. So this is now first the model for a single diatomic molecule and a single triatomic molecule. So for example, lithium hydride and water. So the encoding layer just looks the same for both cases, lithium hydride and water, but for the trainable layer, we just need to choose the qubit pairs differently, which is due to this permutational symmetry in the case of the triatomic molecule. And moreover, this is something I've not talked about before, we can optionally include this yellow part, which is a so-called symmetry breaking layer. So here, this consists of parameterized operations, in this case, Z rotations, which do not respect the symmetries. And we could observe empirically that this can lead to enhanced prediction accuracies. Okay, so for the third case, for the dimer case, the model now consists of 7 qubits, as I explained before. 6 qubits are used to encode the 6 atoms, and the 7th qubit is an ancilla qubit to handle the reflection. And again, we can, if we want, optionally include the symmetry breaking layer depicted here in yellow. The dimer model is actually an important step towards maybe future scaling possibilities to larger sets of the same molecule. For example, a larger system could just be fragmented into subsystems of dimers to learn the overall energy. But this is already a little bit of an outlook. I just wanted to mention it here. Okay, so I've already shown you our architectures that include the necessary symmetries. And now I want to give you a little bit of an insight into our numerical results that we could achieve with this architectures. So first, we considered lithium hydride as an example for a diatomic molecule, and we trained it on exact energy labels. And we did this for both the generic model that was introduced previously, so the generic quantum learning model that did not know anything about the symmetries, and the symmetry-invariant model that we just introduced. And so here on the left side, you can see in the upper panel, the energy prediction for both models. This is just the energy against the interatomic distance for better visualization. And then in the lower panel, you can see the force prediction, where it's just the reference forces against the predicted forces. So it should lie on one line, right? And you can see that the generic model was not able to learn the energy over the total reference data range. So you can see these red triangles, which show us some outliers in the higher energy range. But on the other side, our symmetry invariant model did not show this problematic behavior. So for the numerical comparison, we just excluded this large outliers for the generic model, because in practice, in molecular dynamics, we often rather focus on the lower energy range. So for better comparison, we just excluded those. And if we exclude these outliers for the generic model, it's we can observe that both models still show comparable results for the energy prediction, but our new symmetry invariant model shows an improvement in prediction accuracy for the forces by 1 order of magnitude. So this is already when we exclude these outliers, and our symmetry invariant model is able to perform better for the forces. And at this point, I should maybe stress again that accurate forces are like the main focus within molecular dynamics, because we do not really need the potential energy. In the end, we need the forces. Okay. Next, we trained this model for lithium hydride also on noisy energy labels. And here again on the upper panel, this is the plot for the energy loss, or the loss on the energy prediction for increasing noise. And on the lower panel, you can see the same, but for the forces. And this example of why we did this is that it could be relevant. Such a scenario could be relevant if we wanted to make use of reference data, so energy labels that were generated by a quantum computer. And while before the energy prediction of both models were comparable, here we can observe that the generic model suffers more from the noisy data, and it furthermore fails entirely for the force prediction, while the symmetry invariant model outperforms the generic model in both cases. Okay, so that was our, that was my insight for you for the numerical results for the diatomic case. In the case of a single water molecule, we trained the generic model, the symmetry invariant model, and symmetry invariant model with symmetry breaking. So this yellow layer that I told you about. And we observed that including the symmetry breaking led to a prediction improvement of 1 order of magnitude. And in this figure, you can see a comparison of the prediction of the generic model and the symmetry breaking model that included symmetry breaking. Yeah, that's the symmetry invariant model that included the symmetry breaking. So in this way. And we can see, especially for the forces, that there's a significant improvement if we make use of the symmetry-aware model. So you can see here in the right panel the comparison of the predictions for the forces, and while the blue data, so this is what we get from our symmetry-aware model, lies perfectly on line with the reference forces, the generic model shows a little bit more of variance, right? And again, we are in the end interested in these forces, so this is a good result for the setting of molecular dynamics. Yeah, in the case of a water dimer, this was our last example, we were able to learn the potential energy well, but we also observed significant inaccuracies in the force prediction, which is likely due to the fact that our model was not expressive enough for this more complicated system. And furthermore, this could also be caused due to the fact that we did not include the forces in the loss function yet, and therefore there was a lack of information. Both extensions would require heavier computational costs, which we here want to leave for our future research. But for the specific case of a so-called 1D cut, where we only allow one atom to move, we could already see that including the forces leads to an improvement of force prediction. So this could be a promising way to enhance the current model for the water dimer case. Yeah, as a very short teaser, I would also like to mention that we will very soon release a demo about the implementation of the just introduced model with penny lane. So this is something that I did with my co-author Auriel. So if you would like to have a hands-on introduction to the realization of this work, you can just visit penny lane's demos, and ours should be or should appear in a few days. Yeah. Okay, so I think we have learned quite a lot about the symmetry-invariant quantum machine learning force fields today. So I want to shortly summarize what we have seen. We started from molecular dynamics, for which we require a model that can give us access to the atomic forces in order to simulate the dynamics of atoms or molecules in a chemical system. And we have seen that such chemical systems obey symmetry invariances such as translations, rotations, permutations, or reflections. That means that any model that wants to make reasonable force predictions also needs to reproduce these symmetrical behavior. And in this talk, we are focused on including the symmetries in the quantum model by design. I've shown you symmetry-invariant quantum learning models for the example of lithium hydride, water, and water dimer. And we could see numerically that these symmetry-invariant models show better generalization properties than the generic quantum models, and that they are less noise sensitive if the reference data is a little bit noisy. Furthermore, we observed that actively breaking the symmetry can lead to better training. And while these results show how geometric quantum machine learning could be applied within a chemical setting, there are still many possible directions to go in the future. So as I already mentioned before, systematic fragmentation could be applied to target larger chemical systems of the same molecule. And for this, our dimer model could be an important building block. And alternatively, we could also as an alternative to incorporating the symmetries in the quantum learning model itself, it could also be considered within the training routine, which was recently proposed under the name of symmetric derivatives of parameterized quantum circuits. So that would be a very different direction. Instead of including it in the quantum operations, just use a generic quantum learning model and include it in the training routine itself. Yeah, and another totally different idea could be to use our symmetry invariant models to construct some kind of quantum symmetry functions. So these symmetry functions I have mentioned in the very beginning are just a symmetry invariant description of the configuration. And maybe our symmetry invariant models could be used to create these descriptions of the environment, of the chemical environment, instead of actually being trained as a quantum learning model. Okay, so maybe to put everything into one sentence, chemical and physical systems obey symmetries. So I think it is very reasonable as an approach to let the quantum learning models also know a little bit about this extra information. Yeah, I hope I could give you a little bit of an insight into our work. And thanks a lot for your attention.
Yep, cool. Thanks, Isabel, for the very kind of detailed talk. And yeah, like the way that you kind of ripped out everything and then it's kind of like combines all the puzzles and shows the complete pictures of how to construct things. For the audience, if you have any questions, like feel free to type it in the chat or unmute yourself to ask the questions. But maybe let me start asking a few questions while people are thinking about that. Over here, I'm quite curious on like how easy it is for you to kind of like construct all the gates and like find the observable that obeys like like equivalent or like symmetries and all that properties. And then like whether there are any like technique that you use to do that, because I would imagine if you kind of like scale a system up, is getting hard. It will be getting like harder and harder like for you to kind of construct such a observables or like the gates,
Mhm.
right? Yeah. So do you have
Yeah.
any kind of generic techniques that could allow us to discover all the gates and observables?
Yes, so there do exist general approaches on how to systematically find these equivariant operations. So, for example, the twirling method is very common, where you kind of, yeah, you just kind of integrate or sum over all these over general operations that were kind of sandwiched between the symmetry operations and thereby symmetrize the overall operation. This is also nicely summarized, I think, in a paper by the Los Alamos people that kind of talk or wrote about representation theory for equivariant quantum neural networks. But in our case, I think maybe we were lucky. I teased that already in the talk that we took, for example, the Heisenberg interaction as, or the Heisenberg Hamiltonian as an inspiration, because we already knew that those would be rotational invariants. So in our case, we verified, of course, the invariances and equivariances, but we kind of had educated guess, I'd say. But there do exist systematic tools to find these operations.
Yeah, if I understand those correctly, it seems to be quite hard to do all the calculations in order to find the gates. So I'm just, yeah, I think that educational guess would be the way to go if we don't want to solve all the complicated equations and do the integrations to do. Yeah. Oh, so yeah, Daniel, have questions maybe you have on yourself to ask.
Yeah, thank you for the nice talk. So you mentioned it's less noise sensitive. This means less sensitive to noise in the training data.
Yeah, so in our case, we considered noise on the training data. So we had as a reference data, in that case, we only took the energy labels as reference data, and then we added some noise on these energies. The inspiration for that was that we also had work done on making use of energy labels generated by quantum computers for these force fields methods. And that was kind of the inspiration. Yeah. So we did not consider any other type of noise.
Yeah, because I'm wondering, one of the original motivations for these kind of quantum neural networks was their ability to compensate for gate errors by changing the rotation angles. But if you have equivariant encoding gates, then if you have errors which take you out of the symmetry subspace, you might have trouble getting back.
Yeah, yeah, exactly. So that's also why a lot of people have proposed the symmetry breaking layers, which could kind of, so we would have the information about the symmetries, but for minor deviations or errors, we could compensate by allowing for the symmetry breaking by adding these generic parameterized operations.
Does this also give you a way to, say, assess the error in your circuits by encoding different representations in the input data and seeing how much the output changes?
Yeah, I guess that, I don't know. I mean, it would of course have an effect. Yes. I've never thought about it that way because we always only did, so we did not consider noisy qubits or anything or gates. But yeah, sure. If we would assume that including the symmetries in our quantum circuit would also lead to exact invariance in the output, and it's not invariant, I guess there might be a way of actually quantifying it nicely, the amount of noise that we had in our quantum circuit.
Thanks. And slide 23. I'm just wondering how much training data is, how many training points are used here? Is it?
Okay, so I think I would have to look that up to not say anything wrong. Let me very quickly look that up. So it was around a couple hundred something for the diatomic case, I think.
Okay, so it's really a dense sampling of points, and you're fitting.
In this first approach, yes, yeah. Okay, so the overall set was about 100 something data points, and then for the training we took 53 training points and had I think 80 to 90 testing points then.
Okay, thanks.
Like about this, like along the similar line of the questions that asked by Daniel, I'm just wondering, like what do you expect the scaling of the training data that you need to use when you scale up the your system size? Yeah, because like normally it's so when we have like large system size, I would expect first to have need to have like more access to have access to more training data. But do you have any guess on like how the number of training data will scale with the system size based on your understanding of that? Yeah.
So I don't have an explicit guess. So what I observed was that if we include the symmetries, then the shape of the energy can be learned very nicely already with a few sampling points only. But then when it comes to the finer maybe oscillations in the potential energy surface, of course we need a higher resolution in the reference data, and that seemed to be a little bit difficult now for the water dimer case, for example. So what we observed was that while the energy seemed to be nicely reproduced, the forces were not so nicely or so nice, and this might be due to this more complicated shape of the potential energy surface where more oscillations appear. And I guess for that, one, we need a more expressive model, but also more training points or reference data, which could be one of the challenges, because these reference data is what is expensive, right? So otherwise we could have also just made use of these ab initio methods directly in molecular dynamics, and that's not feasible. So I cannot really give an explicit guess, but it seemed to be for the first try, it seemed to be a little bit challenging. Yeah.
Right. Okay. Yeah, and another question that I have is that the Los Alamos groups recently just released another articles basically trying to say that okay, like if your quantum machine learning models or like variational quantum models in like does not have variables in general, then it might be classical simulatable. So like with this kind of like point of view taking into account, you still think that we need to kind of design quantum machine learning algorithm that respect symmetry or stuff like that?
Yeah, that's a good question. So as I said here in the outlook, I think it is very nice that we know how to construct quantum circuits that respect the symmetries. But I also see that training these quantum learning models is difficult, especially in comparison to classical models. So that's also why I think the last point that I pointed out here for future research, these quantum symmetry functions could be interesting, because here we would not make use of the quantum circuit as a learning model, which we would have to train and thereby always like run several times, but we would just make use of this quantum circuit to kind of give us a symmetry invariant description of the atomic configuration. And then this atomic or this representation could be used in classical machine learning routines, for example. So I think that's a very nice idea of maybe leaving the trainable part or the training part to classical models and make use of quantum models rather to generate inputs that can capture maybe some physical insights that are difficult to capture otherwise currently. So yeah, I think this would be a nice research direction. Yeah.
Right. Basically, it's trying to incorporate some pre-processing methods to enhance the methods and trying to identify identify the parts where like quantum computing could really help instead of like relying just purely on quantum computer users. Yeah, recently there are a lot of like kind of like people just like trying to say is about this like basically the combination of like classical and quantums. Like for example, I know there's one work trying to train a tensor network classically, and then after that we just like compile that on quantum computers to have a good starting point, and then we just like train it afterwards. Yeah, so it's like nowadays it seems like people are going more and more direction to have like good like initializations with the help of like classical computers. It seems like this quantum symmetry functions is going into the same directions, where we are trying to utilize like classical computers or even some like clever way of designing some functions that could like better use of like quantum computers on the task that is good for.
Yeah. So I think so what you just mentioned with the tensor networks and then compiling to a quantum circuit, that would be a little bit the other way around, right? So what I proposed here with the quantum symmetry functions was not that we classically try to construct something and then map it on a quantum computer, but rather have something on a quantum computer that we don't have to train, but that already involves the insights into the symmetries, and then take the output of that to make use of it in a classical computer. So kind of swap the other way around. But
okay, I see. Okay. Yeah, I think for clarification, I think it's it could be a good way to utilize quantum computers, like use it as some way to a lot of people like to say like using quantum computers as a sampler, and then it's like get the samples and then train like classical machine learning models and just like do things afterwards.
Yeah.
Okay. Yeah, I think yes, like now it's 5 p.m. I think. Yeah, so it's we have used up the time. Maybe we can stop end the seminar right now. And thanks again, Isabel, for the very interesting talk. And I really hope like someone could like pick out this direction and trying to investigate all the future direction that you have suggested. That seems to be quite promising, and we need more people to like go to this kind of direction to explore all the possibilities, because like nowadays we would just okay, there's current battles, and then we maybe have to stop while we have to go exhaust all the possibilities before we say that. Okay, yeah, thanks again everyone for attending this, and see you again next week. Bye.
Thanks for the invitation. Bye.